Let's do this. Can everybody hear me? Can everybody see me? How's the transmission? All good. Thank you, Oscar, for confirming. Okay, without further ado, let's do today's third installment of the On Request webinar, which means that I'm going to share my screen and let's go to the content. So there we go. Today is another instance of at the on demand, which means that in the Meyer Sound user community Facebook group, we offered a poll where you would get to vote what it is that you would like us to talk about today. This time there were 3 options for you to choose from, which was Montreux Jazz, B-Noise, what I'm saying, M-Noise, and the third option on the menu was Frontfill systems. And the vast majority of you would like us to discuss Frontfill systems, so that is what we will be doing today at your demand. Frontfill systems, which is what is going to be today's focus. But before diving off the deep end, let's look at a few household notes first. Starting with Zoom. We're using the Zoom communication platform to conduct these webinars, and that means that in front of you, you should see a window not unlike the one you have in front of you right now. If you want to see who else is joining you on today's call, please click on the participants button, in which case a window will pop up on the right side showing the fellow attendees. We encourage you to ask questions, but in order to do so in an organized fashion, we would very much like you to make use of the raise hand feature. Notice the gray button at the bottom right corner of the screen, which says raise hand. If you click that button, a blue hand icon pops up in the corner of my eye, informing me that you're about to ask a question. In order to ask the question itself, we encourage you to make use of the chat function. Now, in order to activate the chat function, all you have to do is click on the balloon icon, which will split the right-hand pane in half, bringing up a chat dialog. At the bottom, there's a field where you can enter a message, and then you can address the nation, that is to say everyone on the call, or if you happen to see a friend, colleague, or family member, you can also address a message to that person in private. That pretty much concludes the household notes, which means that we're going to continue by looking at today's checklist, the checklist of things that I intend to cover today. For those that are joining us through Facebook, welcome to you as well. Currently counting over 8,750 members and growing, so welcome to you as well. This is where we're simulcasting, and we're happy to have you as an audience. This is going to be another episode that discusses the turnkey solution, which is our precision toolset from design to deployment and monitoring and much, much more. We've been talking about this for over 5 weeks of webinars that we've been conducting now. And today is going to be another edition. Today we're going to talk about Frontfills, which means that we're going to use map to look at some predictions and how to space your Frontfills in particular, which means that there are several webinars that come in handy in preparation for today's webinar, starting with, of course, the introduction to MapXT, which we conducted a long time ago. Then there was down-tilt translation, where we introduced the concept of triangles and multipliers, which we will use a great deal today. How to import CAD files, computer-aided drawing files, into MapXT. And then earlier this week, last Wednesday to be precise, we did a case study of Lena and House of Worship. And a lot of the concepts that we covered over there will show up today once more. Very important, more important than the other 4 at this point with respect to today's content is the last on-demand webinar, or the first, I should say, the first on-demand webinar, where you asked us to discuss power scaling. So today we're not gonna discuss power scaling. We're not gonna discuss how to choose the ideal companion Frontfill loudspeaker to your main PA, because that's something that we discussed in previous webinar. Today I would like to emphasize more at how to space a given loudspeaker once I found the appropriate companion loudspeaker to complement my main PA. So today is more going to be about spacing, how to determine the correct element. For that, we would like you to go back to that particular webinar called power scaling. Okay. All of those webinars can of course be found in our YouTube channel, which is called Thinking Sound. There you will find those 5 webinars that I just mentioned and many, many more. So please be sure to visit that YouTube channel to catch up with those prior webinars. So I made a checklist. I've got my pen ready. And the things that I want to discuss today are sonic ventriloquism. I want to talk about fresh and intelligible mid and high frequencies, aux-fed submixes, occultation, what are foot fills, and then triangles and multipliers, as I already indicated before. And then we're going to look at an example of straight arrays, and we're going to look at an example of arched arrays, where the proscenium might be an arch. We're going to look for that. We're going to look at those configurations in map and see how to determine the appropriate spacing. Okay, so what do I mean by sonic ventriloquism? What is a reason that you could consider using Frontfills? Because Frontfills is one of those subsystems that, at least for very few people, has the potential to pull the image into the general direction of the subject on stage. Because the Frontfills, as you know, live on the edge of the stage, which means that in the vertical we can come down, we can come out of the main PA, out of house left, house right, can come down in the vertical. And because we get to put them on the stage or close to the stage edge, it also allows us to pull the image inwards, towards the subject, towards the general direction of the subject, hence sonic ventriloquism. So it favors localization in favor of typically what are money seats. In most venues, the first couple of rows are the most expensive seats in the house. So those Frontfills loudspeakers really serve a purpose for that part of the audience in terms of localization, but also in terms of adding fresh and intelligible mid and high frequencies, as we're about to discover. Because in a conventional left-right system, there is this typical area where you're in the center of the house, as you can see on the left side of this slide. There's this typical triangle, this region, where you are underexposed, where left and right haven't met each other yet. You have to venture further towards the back of the room before that gap is closed and left and right meet each other in the middle. So that's a very common area where we are lacking mid and fresh and intelligible mid and high frequencies. Now, at the same time, at the lower frequencies, if we go to a 1-octave prediction center at 63 Hertz, where functionally all systems tend to be very much omnidirectional, we have the power alleys and the power valleys that we discussed during the previous webinar, Lena in the House of Worship. So in the middle of the audience, in those first couple of rows, the only thing that's typically not missing are low frequencies. Those few spectators are sitting on the top of a landslide, of an earthquake, and the only thing that there's missing over there are fresh and intelligible mid and high frequencies, which is yet another reason to specify Frontfills, because it's one of the few systems that can get to those, typically money seats, can get to those seats and restoring all information that was missing. But while doing so, we have to be mindful of occultation, as we're about to discuss. About to see. That being said, it could also be that there is too much of a particular part of the mix. For those that do rock concerts and such, typically the only thing that's not missing in the first couple of rows might be guitar, in electric guitar in such a scenario. So those same Frontfill loudspeakers can also be used to deliver a stem or several stems or several mix elements without adding more of the elements of which there's already abundance in those first couple of rows. It would also mean that we have to matricize our channel delivery, and of course there is an entire webinar that discusses channel delivery using matrices to do exactly that, to deliver a submix an aux-fed submix or from a matrix on the console level, but delivering a mix to those front fills, which contains everything except for the electro guitar, for example, like we're seeing over here. So there can be many applications that might require or can benefit from having front fills. That being said, we need to be mindful of occultation or acoustic shadow, because a human body, let's start with the human head. The human head is on average is the size of about one wavelength of 2 kilohertz, which means that if there's too many spectators between you and those front fills sitting at the edge of the stage, if there's too many spectators, then the very frequencies that are missing in the start of the audience, which are those fresh and intelligible mid and high frequencies, might be occulted once the seats are occupied by human heads. The same is true for a human torso. Human torso is about one wavelength of 800 hertz, which means that all frequencies above 800 hertz whose wavelengths are shorter might be occulted by the presence of a human person, a body sitting in a theater seat. And then regardless whether the house is full or that the house is empty, the backs of the chairs are of similar dimensions as a human torso, which means that if the front fill loudspeakers cannot live on the edge of the stage, but due to cosmetical reasons have to live in the stage lip, then very often we like to joke that they become foot fills. But it also means that they're firing into the backs of the chairs, and regardless whether the house is empty or full, now those very frequencies which are missing in the front of the audience typically are in trouble, are in danger of being occulted, regardless whether the seats are empty or occupied. So this is also something that you have to be mindful of. Whenever you design a front fill system, be sure to check your line of sight, or as we like to say, your line of sound. Can I see those high frequency transducers? Because they are responsible for adding those fresh and intelligible mid and high frequencies. So today we're going to talk about triangles and multipliers. Now this might be novel to some of you. That's why we deferred to the down tilt translation webinar earlier today, because we're going to look at a lot of triangles in today's webinar. And while doing so, I will remind you a little bit of what that multiplier and that triangle was all about. That being said, any loudspeaker can serve as front fill, goes without saying. However, in practice, some choices are more obvious than others, which means that rarely do you see a Leo element as a front fill. Same goes for Lion. That being said, depending on the scale of an event, you might find a Leopard or a Lena being used as front fill. Same goes for Ultra series. Could be an Ultra X40 or an Ultra X20 or a UPM. And then there's the Intelligent DC series, where we did an entire webinar on which are our external powered loudspeakers, such as UP4 Slims, UP4 XPs, and MM4 XPs, where XP stand for externally powered. Notice that, that being said, that in the Ultra series, I put a little asterisk behind the X20 and the UPM, because those loudspeakers can also be used in conjunction with a power supply, can also be used externally powered. That's why I put the little asterisk there. These are your usual suspects, and of course all these loudspeakers have various coverage angles depending on how the horn is rotated. They might have various coverage angles, typically anywhere from 50 degrees at its narrowest to as much as 110 degrees, such as a Leopard. And with each of those coverage angles, there's a multiplier involved that we discussed during previous webinars that will also show up today. So that brings us to the part where we're going to look at how to, emphasis today on how to space the front fills depending on whether I have a straight stage edge or whether I have a curved or an arched stage edge. And before doing that, I would like to start with section view. So here we see a map. On the left side, we see the stage indicated by orange. So if I highlight that, then over here we see the stage area indicated by orange. This is a section view, which means that you're looking on the venue from the side. On top of it, we have a single front fill loudspeaker living on top of the stage. over here in a pinkish magenta color. And then we see the first row, we see the second row, we see the third row, and we see the fourth row of our audience. And at this time, because the values might appear to be a little bit small, at this time we're dealing with a displacement, a distance between the edge of the stage and the first row. This is currently 2 meters. And then we have another row every 1 meter from there on. So 1 meter spacing between the rows and a 2 meter air gap between the edge of the stage and the first row. In this example, which is not uncommon, the listener's ears live in what we call the propagation plane. So if I were to highlight the propagation plane of today's loudspeaker, then this is the propagation plane. That is the two-dimensional plane where the sound propagates. And notice that our listeners with their ears are living in this propagation plane. And that raises the question, do we experience any angular attenuation in the vertical? Now, what do we mean by angular attenuation in the vertical? Our loudspeaker has a coverage angle. It has a 80-degree horizontal coverage angle in this case, and it has a 50-degree vertical coverage angle. So the arrows that I'm drawing currently, that is the 50-degree vertical coverage angle from off-axis at the bottom to off-axis at the top. And what happens when you live at the edge of coverage? When you live at the edge of coverage, you get 6 dB of angular attenuation due to your listening angle with respect to the loudspeaker. And the same is, of course, true at the bottom. Whether we experience this remains to be seen. That being said, I would like to show you this a little bit in action, which means that we're going to do a prediction. Let's do 1 octave at 4 kilohertz and look at the level distribution throughout our audience. So, what are we looking at? Imagine that we call this transition from a very saturated orange to a lighter orange color. Imagine, and let's do the following thing. Let's change the color to something which is easier to see. Let's use a black color. So let's call this transition. Today, just because we can, let's call it 0 dB, because during previous webinars we explained that we like to work in 3 dB color divisions. If we call that 3 decibels, then if we go up or down angle with respect to a loudspeaker, we start to lose a level, we start to lose market share, because the next color transition would be a 3 dB drop, and the next color transition would be another 3 dB drop. The same is if we go down angle, then that is going to be a 3 dB drop, and another color division is going to be another 3 dB drop. So there you see the vertical coverage angle, the 6 decibels of angular attenuation that I mentioned first. And now the question becomes, do I experience this as a spectator? And the answer is no, you do not experience this unless you stand up or unless you lie flat on your belly on the floor. But as long as you remain seated, you're not going to undergo any of this angular attenuation as a function of height, as a function of angle, unless you stand up or lie on the floor. And that means that this vertical coverage angle, in the example that we're looking at right now, this vertical coverage angle plays no part in the cross section that we're currently looking at. So what does play a part? What is something that we need to be mindful of? Well, we need to be mindful of distance, because there's also another phenomena which is known as the inverse square law, which states that if you double your distance, you lose 6 dB market share. Your level drops by 6 decibels. Which means that if we go to the first row and we refer to that as 0 decibels, which we get to do, that is our prerogative. If we call this 0 dB relative, then we get to double our distance once, which is saying we get to go from 2 meters to 4 meters. And by the time we are at 4 meters, we will have lost 6 decibels because we doubled the distance. And that point in space indicates the expiration date of our Frontfill system. Not for a lack of trying, but because you double the distance and you lose 6 decibels of actual gain due to the inverse square law. And that means that in this particular example, come 4th row, or I should say come 3rd row at 4 meters distance to the stage, we raise the white flag, and we will ask for reinforcement, which means that somewhere around the 4th row, either the main PA coming from above needs to touch down, or an infill coming from a side, but we need reinforcement from another system. It's not that the Frontfills stopped working, it's just that as you went from the 1st row at 2 meters to the 3rd row at 4 meters, you lost 6 decibels of level, and hopefully by now another system, whether it's your main system or subsystem, meets that point in space at -6 dB relative level as well, so that -6 and -6 together in unison will restore the level to 0 decibels in a team effort. So in an application like this, that distance between the edge of the stage where the loudspeaker lives and the 1st row is a very important metric, because that distance times 2 will provide you the throw capability, for lack of a better description, the throw of your Frontfill system. Because, as we discussed before, the vertical angle does not play a part in this particular exercise. So if it's 2 meters to the 1st row, your Frontfill system will work perfectly fine up to 4 meters. However, if it's only 1 meter to the 1st row, then by extension, your Frontfill system will only work up to 2 meters. Conversely, if it's 4 meters to the 1st row, your Frontfill system might work all the way up to 8 meters, provided that there's no occultation. That is to say, provided that there are no human bodies or heads or torso or backs of seats between you and those high frequency transducers. And I hope by now that everyone is able to appreciate that when the loudspeaker no longer lives over here, but due to cosmetical reasons is expected to be mounted in the edge of the stage, which is not that uncommon, that it's pretty much game over after the 1st row, because now, regardless whether those seats are empty or are occupied, with the occultation that we're dealing with now, really diminishes the success chance for such a Frontfill system. And that means that now, come 2nd row, you really need a reinforcement from another system to account for the occultation that the Frontfills suffered from due to the obstruction of the 1st row, the seats in the 1st row, and to make matters worse, once those seats have been occupied. And that is why we like to joke that when the loudspeakers are expected to live in the stage edge, we prefer to call them footfills, because they're basically there to cater your feet rather than your ears. But that is just all tongue in the cheek. So that is the deal in section view. Now I propose that we abandon section view and make a change to plan view. And the first plan view that I would like to look at is the classic example of a loudspeaker living on the edge of the stage, trying to cover that 1st row. So for everybody to be on the same page, our stage is in the bottom. This is where our stage is, and our audience lives over there. This would be your 1st row, and then if we go up, then we see the 2nd row, and we see the 3rd row, and so on and so forth. So our audience progresses in that direction. And the question becomes, do I have to be mindful of the coverage angle in the horizontal plane? Because I use these magenta lines to show you the 100-degree coverage angle that goes with this particular loudspeaker. That is a 100-degree coverage angle. And that is what you will find in the data sheet, because that coverage angle is the rule and not the exception. Today it happens to be 100 degrees, and it remains to be seen whether this is the ideal construct, coverage angle, that's to say, the radial definition, whether that's the ideal construct to now start thinking about the spacing of my loudspeakers. Because if we now look at a prediction and look at 4 kilohertz, 1 octave, those fresh and intelligible mid and high frequencies, then knowing that ever color division is a 3 dB drop in level, we now clearly see that in this case, unlike the vertical, that in this case, the horizontal angle at which you're listening, of course, is super important, is very important. Because if you're in the middle, then you're on axis to the loudspeaker, staring the loudspeaker in the face, you're good to go. But as you abandon those center seats and start to make your way in either direction, now you start to see a drop in level due to angular attenuation, because you go from on axis to off axis. So now where you are sitting with respect to that loudspeaker will determine what level you're exposed to. And the challenge now becomes, can we use several of these loudspeakers to make the, as it's known, uncoupled line source, because the loudspeakers live on a line, to make the uncoupled line source take care of those other seats as well. Now, what is the rule and what's not the exception? When we start talking about spacing, what is what you typically will see? Very common. People are inclined to say, well, you know what? Our loudspeaker has a 100-degree coverage angle, so I need to space the next loudspeaker next to it so that the off-axis trajectories, if you will, so that the off-axis trajectories meet each other by the time we reach the first row. So notice that I've used the copy-paste feature in MapXT. That allows me to copy and paste, as the word implies. Let me try to make those colors the same by assigning those loudspeakers to the proper layer. And this is logical reasoning. A lot of people will reason that this should work because, after all audience members in those first seats are within the coverage angle of a given loudspeaker. So that looks very promising. So far, so good. But now it remains to be seen whether this will actually work. So let's clear the annotation and let's do a prediction when we start looking at 4 kilohertz. So now I see all of those 3 front fills at once. They're fired all up. They're showing a 4 kilohertz octave at 4 kilohertz, that's to say. And sure, it looks very promising, but let's be a little bit more discriminate. I'm going to start drawing on top of this, and I'm going to start with this color transition. That is to say, where we see the change from red to orange. And I'm gonna christen that 0 dB. Because we can. So I'm going to call this once more 0 dB relative. That's going to be my 0 dB relative. And now I want to start looking how many colors can I move, or I should say how many seats can I move over until I lose 6 dB market share. Well, if we call this transition 0, then this is 3 decibels and this is another 6 decibels. And of course I can move the same amount of seats in the other direction. 3 decibels, 6 decibels. Okay, let's do the same for any of those other 3 front fill loudspeakers. Starting over here, if I draw that arrow in one go, then unlike what you might have thought, it clearly shows that the spacing between our adjacent front fills is too large. We do not have -6 meeting -6. What do I mean by that? We have -6 dB over here. We have -6 dB over here, relatively speaking. We have -6 dB over here. Of course, we have -6 dB over here, and by the edge of the screen, we have -6 dB over there. But notice that they do not meet each other in the middle. That is to say, they do not meet each other at these points in space where our coverage angles intersect. And for those that find it hard to see, this was one coverage angle. This is the other coverage angle. And the same is true over here. This is one edge of coverage, and this is the other edge of coverage. They're very much intersected at the first row, and yet we can clearly see by looking at the level distribution that we have level variance in excess of 6 dB. So, while I was explaining this, there's a question in the chat from Marsban who says, why choose simulation at 4 kHz and not 2 kHz? Because this exercise is only interesting to do in that part of the spectrum where the loudspeakers are directional. If you want to see whether you're aiming the speaker in the right direction, sending the sound to where it needs to be, then you would look preferably in that part of the spectrum where the loudspeaker is well behaved in terms of directivity. If we look at low frequencies, then all of these loudspeakers are expected to be omnidirectional, and that means that at those frequencies there's very little for me to see in terms of, do I have the correct spacing between the loudspeakers and are they aimed correctly? So that's why we look at 4 kHz, because it of course depends on the size, the dimensions of the constant directivity horn that's used, which means that for a small loudspeaker with a small horn, you might want to look at 8 kHz. For a medium-sized loudspeaker, you would look at 4 kHz, and for a large loudspeaker and very well behaved, such as the Ultra X40, you could look at 2 kHz as well. Out of the gate, for most applications, we recommend to look at 4 kHz, 1 octave, because that's the typical frequency range where your loudspeakers are very well behaved. Needless to say, they're also well behaved for other parts of the spectrum, but in terms of aiming and spacing, 4 kHz is your common departure point, according to our recommendation. So the approach of spacing these loudspeakers based on their coverage angle, which I will find in the specification sheet, doesn't give me the required spacing. I end up getting gaps, air gaps between adjacent loudspeakers that are too big. So let's look into that a little bit more in depth. Let's single out a single speaker and look at the level. Like before, you will see that this is the width within plus minus 6 dB. But according to the coverage angle of the loudspeaker, theoretically, you and I should be capable to cover this much width. That is to say, from off-axis on one side in the first row to off-axis at the other side in the first row. And yet, once we look at a prediction, we see that this is not true. And on either side, we are 2 seats short. We're missing 2 seats over here, and we're missing 2 seats over here. And once the brothers and sisters come into play, like we saw in the previous example, once those brother and sisters come into play, we're gonna lose another 2 seats on their side as well. So we had 4 seat gaps between adjacent loudspeakers. So somehow using the coverage angle as a departure point doesn't work, because the usable width, the width that we actually get to exploit, is 2 seats less on either side. And for those that watched previous webinars, they know that this is the famous triangle that we've mentioned during a previous webinar. It's upside down, which means that the base of the triangle currently lives over here, and the tip of the triangle lives over here. So the triangle is upside down, but in previous webinars we learned that there's a way to predict the width of the base of that triangle. So if we refer to this as the base, then we can determine the width of that base. We can predict it in advance depending on the height of the triangle. And the height of the triangle is determined by the distance of the tip of the triangle to the base of the triangle come first row. And that's where your multiplier comes into the equation. So if we go briefly back to the keynote and bring up that table once more, then the table shows us that when you're a 100-degree loudspeaker, like the one that I'm using in this example, when you are a 100-degree loudspeaker, then the multiplier that we're looking at is shown over here. Rounded down to the nearest value would be 1.5. So if you're a 100-degree loudspeaker like we're using now, then the multiplier becomes 1.5. Now what does the 1.5 mean? The 1.5 means that if I know the height of my triangle, which you do, then you can predict the width of the base. So let me make that diagram once more. This is the height of your triangle. Let me use a different color. This is the height of the triangle to the first row. We already figured out that this was the width of the base of the triangle. This is the completed triangle altogether. And if you want to know the width of that base for a 100-degree loudspeaker, all you need to do is multiply the height of the triangle times whatever multiplier, which is 1.53 for a 100-degree loudspeaker, times whatever multiplier to discover the width of the base of that triangle. So in this case, if it is 2 meters from the loudspeaker to the edge, at the edge of the stage to the first row, if it happens to be 2 meters, then the width of the base will be 3 meters. If it is 10 meters, just as an example, then the 10 meters from the first row to the loudspeaker, then the width of the base will be 10 times 1.5, will be 15 meters. If you want to know more about that, be sure to watch the down tilt translation webinar. So why do we not get to use that coverage angle all the way from this point in space to this point in space? Because you're getting a double penalty. Now, what do I mean by double penalty? As you abandon the center seat and start to move towards either side, you're going off axis, which means that you get your first penalty. If you go off axis, you get what we call angular attenuation. That is strike one. You're going off axis, so you get attenuation, which is determined by your angle with respect attenuation with respect to the loudspeaker. But you're going to get a second penalty as well, because as you started to move off axis, you also covertly start to increase your distance, and that is going to be your second penalty. And that means that on top of your angular attenuation, you are now also going to get your inverse square law, and that means that your losses, your pressure losses as you go out of the center, are going to be more than you would expect based on angle exclusively, because you went off axis and at the same time you increased your distance. So that is why you do not get to use the 100-degree coverage angle. In this case, you would only get to use 75 degrees. And we call that shrinkage. So let me show you what we refer to as the effective coverage angle, the usable coverage angle that is left over every time you go lateral. I've already prepared that, and that means that if I unhide this layer, then you will see the usable coverage angle whenever you make a lateral move. Now, what do I mean by lateral? By lateral, I mean when you go off axis, perpendicular to the loudspeaker. Perpendicular to the loudspeaker, you go off axis in this direction, perpendicular at a 90-degree angle. And whenever you go lateral, perpendicular to the loudspeaker, the remaining coverage angle will be smaller than the coverage angle defined in the data sheet. And those losses can be substantial. Those reductions can be substantial. In this case, our 100-degree loudspeaker, according to the data sheet, according to its radial definition, the 100-degree coverage angle is shrunk to 75 degrees, which means that I have about 25 degrees less to play with. That is going to be 12.5 degrees on that side, and it's going to be 12.5 degrees on the other side. And if I'm not aware of that, my front fills are going to end up living too distant from each other, and then I get the problems that we saw earlier. So, with this new metric, the triangle in mind, now we can start to space our loudspeakers in such a way that there will be no gaps between adjacent seats. So let's use the triangle to determine our spaces, which means that I'm going to temporarily kill the off-axis trajectories, and now I'm going to select my loudspeaker, and the triangle, which we now hopefully understand, I'm going to use this to copy-paste. And let's now space our loudspeakers using the triangle so that the corners of the triangle touch each other, come first row. So let's add another one. I'm just copy pasting, add another one, okay, and make those guys intersect, come first row. Okay, that one is going to fall off of the map because my prediction is not wide enough. So I'm gonna let's skip that guy. You get the idea, hopefully. So let's kill that guy and let's look at the ones that we have now. And here's what I propose. Why don't we rearrange these and do it like this? Okay, that at least allows us to cover the entire first row. So let's do another prediction using the triangle as a departure point and 4 kilohertz. Okay, and now you see that come first row, if you look very closely, you see the same shade of orange everywhere, and the same shade of orange over here, and you see the same shade of orange over there, and you see the same shade of orange over here, and you see the same shade of orange over there. You see the same shade of orange, which means that the line is now what we call closed. The line is closed, come first row. How many loudspeakers do you need? Well, that depends on the width of your triangle, and it depends on the width of the stage edge. It depends on how wide of a stage you're using to cover how wide of a row. Notice also that if we increase our distance now 2 times, that we go to the next color transition from orange to yellow, and that shows us the expiration date of our Frontfill system. And as we saw in section view before, that means that if the first row lives at 2 meters, we get to go to 4 meters, and notice that the entire system now drops by 6 decibels over distance, and then we raise the white flag and we say, help, we need reinforcement from another system. So this system, which is known as an uncoupled line source, is the ideal system for an application which requires lateral extension. I need more width than a single speaker. I need more width than a single speaker can provide. A single loudspeaker provides me the following width. Now I need more of that. I need a lateral extension. This width doesn't suffice. My width is missing all of those seats. So now I just need to add elements next to each other. I need to have the lateral extension until I cover all the seats in the first row. So if you understand the triangle, then this is a very straightforward process. Meanwhile, I see a question in the corner of my eye, and the person is asking, is the shrinkage frequency dependent? Yes, the shrinkage is frequency dependent because the coverage angle of the loudspeaker is frequency dependent. That being said, most loudspeakers have a well-behaved constant directivity horn or CD horn, and that means that for half of the audible spectrum, this will persist, this will be very well behaved, and that half of the spectrum, which are your fresh and intelligible mid and high frequencies, that is where we need this to be well behaved, because those are the very frequencies that are typically missing in those first couple of rows, where you typically end up shelving, if not cutting the low end altogether, because you have too much coming from above, from your main PA, or from the subwoofers living in front of the stage. Too much of those frequencies in those first rows anyway. So it's basically everything above 1 kilohertz that you would like to be well behaved, and this is true for our products. Okay, so that is an example of using the triangle to figure out the spacing between adjacent loudspeakers, when the edge of the stage is straight. Of course, you very often find yourself in a situation where the edge of the stage or proscenium is no longer straight, but might be an arc. So in order to demonstrate that, I have made a second map file where I already prepared the triangle. For those that watched the Lena House of Worship webinar, you might recognize this venue, because that's the same venue that we're looking at over here, and it's a fan-shaped venue, which means that this is the origin of what is known as a sector. It's a slice of pizza. This is the origin, and we have a fan-shaped room, and we're only seeing first couple of rows. And now the edge of the stage is no longer straight, and the question becomes, how do I now need to space those front fills and close any gaps come first row? Well, we're going to use the triangle. We're going to use the triangle to do so, because if you have a circle that consists out of discrete points, such as a hexagon is not a perfect circle, but as the number of points increases, then ultimately it will become a better and better approximation of an actual circle. So in a hexagon, this part, which is not circular but a flat top, is known as a chord. But we can stitch those chords together and still come up with something which is a very good approximation of a circle with a fixed radius, a sector with a fixed radius. But in order to do that, we need to make use of the convenient pivot tool in MapXT, because I'm going to select my loudspeaker in triangle, and now I'm going to click on the pivot tool. And that would allow me to rotate the loudspeaker around a given pivot tool. But the pivot tool allows me to choose my pivot point any way I see fit. It doesn't have to be where it ends up by default. And that means that now I'm going to exploit the origin of our fan shape. And if I now start click dragging, notice like the dial of a clock, I can now aim that loudspeaker while tracking the edge of the stage. Notice that the loudspeaker, like a magnet, is sticking to the edge of the stage by choosing a carefully chosen point as pivot point. And now it becomes rinse and repeat, which means I'm going to copy, Command C, I'm going to copy what I've selected, I'm going to paste it, and I'm going to paste it in the original position, and now I'm going to pivot it until the tips of my triangle touch each other. And then I'm going to paste again, I'm going to paste it in the original position using Command V, and now I'm going to rotate this until the tips of the triangles touch each other. And I can even select 3 of these at once, 3 of these chunks, copy them all together, put them on top of the previous 3, go to the pivot tool, and pivot the entire batch 3 at once until the tips of the triangles meet. And notice that using the chords, I was now able to make the tips of the triangles meet. So I have a chord over here, I have a chord over here, I have a chord over here, a chord I should say, I have a chord over here. But those chords together are a pretty good approximation of a circle with no gaps, because that's what the triangle doesn't allow for. With no gaps come first row. And strictly speaking, I have one loudspeaker too much, because one loudspeaker over here fell out of the boat. So why don't we fix that? Why don't we fix that by selecting all our loudspeakers at once? We're going to select all our loudspeakers at once. We're going to go to our pivot tool, and we're just going to rearrange those guys in one go and maybe do this. If we do this, then from wall to wall, from outer wall to outer wall, we have now good coverage. From outer seat over here all the way through the first row to the outer seat over there, the line is now closed with no meaningful gaps whatsoever. So let's look at a prediction for such an approach. And notice that again, there is no more than 6 dB of variance. If you pay very close attention to shades of orange, then if you know what you look for, you will see the same shade of orange. So we have orange over here, but I see 1 pixel, which is all that I need of the same shade of orange over there. Orange over here, same orange over there. Orange over here, okay, same orange over there. Which is all the indicators that I need to tell me that the line is closed. We have a unity level across the first row. Some of you might be thinking, okay, very nice, but I think, you know, if this were a real commissioning of a system or real design, I think we could, you know, save ourselves a speaker. because notice that there are moments where we're catering the aisles between the loudspeakers rather than the people that live between the aisles. Notice that there's an aisle over here where nobody lives, there's an aisle over here where nobody lives, there's an aisle over here where nobody lives, and there's an aisle over here where nobody lives. So why, why cater those areas when nobody is living over there? That being said, if this was a closed fan shape, that is to say with no aisles between adjacent seats, this was about the number of loudspeakers that would be required based on this particular coverage angle to make that line closed. That being said, if I want to exploit those aisles, then we can get away with killing one loudspeaker altogether, and then we just need to make sure that the other guys are catering each of those 5 audience blocks, and then 5 loudspeakers will get the job done. So let's start by re-aiming this guy. Okay, so let's use the pivot tool and put it at the origin, so that guy is expected to go over there. Okay, let's go to the next group. Let's use the pivot tool and aim those guys over there, just in the middle of that sector. Let's go to the next group. That one speaks for itself. That's going to go to its original position, which is over here. Let's go to the next group and orient it in such a way that it goes into its sector. And let's go to the final group, house left, and aim it to its sector. It should go over there. Sure, if you were to look at this, you will have gaps because the tips of the triangles are not touching, but we can get away with that because where we have the gaps, no audience members are living, so this could be very well done. This could be very well done with 5 rather than 6 loudspeakers, as long as the aisles are there. And if we look at the prediction, then this will work perfectly fine. Nobody sees any level variance in excess of 3 decibels. Just look at the tips of those flames. If I start drawing on top of them, okay, if we call the orange color the 0 position, then we have 3 decibels of variance over here. 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 And we have 3 decibels of variance over here. And we might have a little bit of underlap in the aisles, a little bit of underlap over here and over here and over here, but nobody is sitting there, so we're going to put that to good use. So knowing your triangle, using the pivot tool, this is very straightforward, tried and tested method of coming up with the spacing between adjacent loudspeakers. Regardless whether the edge is straight, as we saw in the previous example, or whether the edge is arced. If you know the triangle, you can figure this out in very little to no time. And that concludes, as far as I'm concerned, that concludes today's Frontfill system, where we did not look specifically at which loudspeaker do I need in terms of power requirements, because we already dedicated a webinar on that. But this one looked specifically at how should I space these loudspeakers so that there are no gaps between adjacent loudspeakers. As always, this webinar will be uploaded to the YouTube Thinking Sound YouTube channel, Meyer Sound Thinking Sound YouTube channel, and that means that I'm more than happy to spend a couple of minutes and try to answer your questions to the best of my ability. But in order to do so, please make use of the chat function so that I can read your question out loud and then try to answer it. Interesting. So, question shows up. What application do you use for the arrows? Well, that is the annotation feature that is built into Zoom. So that is something that we have Zoom to thank for. I'm making use of that to draw on top of what I'm trying to show you. Can you apply the same principle for under-balcony loudspeakers? Of course, because the uncoupled point source, the uncoupled line source, which is your loudspeakers living on a straight line, doesn't discriminate whether they live on stage or under the edge of a balcony or an over balcony or surrounds. So yes, you can use the same approach for those kind of applications. Whenever you have loudspeakers living on a line, that is what you can resort to. Is the multiplier the forward aspect ratio of the loudspeaker? No, it's not. And if you want to know more about that, be sure to Google it. It's not hard to find. Any other questions? Merlijn, when are you hosting more webinars? Well, for the past 6 weeks, we've been doing 3 webinars a week. Monday, Wednesday, and Friday in English, and Tuesday and Thursday in Spanish. So next Monday, we're going to do another webinar, which we're still preparing very much. So I hope to disclose that very soon. But we have 3 webinars next week and 3 webinars the week after that. Then I see a question, one delay to all front fills or each speaker different delay? That's an interesting question. We already talked about that when we looked at channel delivery, matrixing. The thing that you of course always have to be mindful of, which we also discussed in that webinar, so be sure to go back to that webinar at your discretion. The thing to be mindful of, and let me temporarily share my screen to answer that question, is what am I gaining and what am I sacrificing? Because there's no such thing as a free lunch. We know that most likely somewhere off screen, over here there is house left, somewhere off screen, and over here sooner or later there's house right off screen, main PA. And now we have several options to choose from, which is okay. If we use one delay for all 4 front fills, so all 4 front fills receiving the same electronic delay, what is preserved? Well, what is preserved by doing that is the connection between adjacent loudspeakers. So by giving them the same delay, the seam between adjacent loudspeakers is preserved, because everyone that lives in the median plane between 2 of those adjacent loudspeakers is equidistant to those loudspeakers. And that means that the timing between adjacent loudspeakers is preserved at the edges, at the seams between adjacent loudspeakers. What is the trade-off, however? Well, the trade-off is that in the sole custody of each of these loudspeakers, in the sole custody of this loudspeaker over here, and the sole custody of that loudspeaker over there, sole custody of that loudspeaker over there, sole custody of that loudspeaker over there, now house left and house right will not be perfectly time aligned, because if house right is time aligned over here, then it will be late over here. And conversely, if house right is in time over here, then it will be leading over there. And of course the same is true at the other side. How could we fix that? By giving the outer guys, outer front fill loudspeakers, that's to say, by giving the outer guys a different delay from the inner guys in this case, which would then allow us to properly synchronize each individual front fill with respect to house left or house right in the area where the front fill is sole custodian. The trade-off is that you now sacrificed the alignment between adjacent loudspeakers. This is now, that one is still perfectly fine, but this is now no longer aligned. And now you have to make a choice and choose wisely. But I've done either, and you just have to be mindful of what you're gaining and what you're sacrificing in such a scenario. So hopefully that answered your question. Any other questions at this point? If not, then I hope to see you this Monday. That's to say next Monday, during the next webinar. Okay, well, in that case, please remain healthy, please remain safe, best to you and your loved ones, and see you soon. Bye-bye.